Hello, my name is Andrew Rush, and this is my Physics 2212 Lab 3 over circuits. For a brief table of contents, we're going to have an introduction, the physics principles used, a resistor circuit experiment, the experimental images and tables, and then the RC circuit experiment. Then we're going to go through some discussions and conclusions. So an introduction. So the purpose of this lab was using the principles of energy conservation like the loop rule and current conservation. We will predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. So then, as you can see here, here's some fundamental principles used. Here's a quick overview of our results, all of which we'll go through later in this experiment, or in this lab. Here is a this is the RC circuit, and this is the other experiment that we conducted. So like I said, here are the physics principles. So we used Kirchhoff's current law, known as the node rule, and his voltage law, known as the loop rule. And then Ohm's law, where V equals IR. Current of IC circuit is negative dQ over dt. The voltage of an RC circuit, and DCSS behavior. So the circuit drawing, so our system was a full circuit made with resistors, voltage sources, wires, ammeter, and voltmeter. Our surrounding was the earth, and some assumptions we acted upon in this experiment was that all wires have zero resistance. All resistors and voltage sources have exact values. Some predictions that we had for this experiment was that the actual loop resistance calculated will be greater than zero, and a higher resistance yield longer charge and discharge time. So the R circuit experiment, the procedure here was to assemble the circuit using resistors, batteries, and ammeters, as you can see in the drawing. Our I1 was 16.96, and it's negative when reversed because power and ground switched. Our voltmeter connected was 2.92 volts and 0 amps at the ammeter. Voltmeter has an infinite resistance, so no current passes. Positive voltage because voltage straight from the battery, comes straight from the battery. Our R1 was negative 1.8 volts, and R2 was negative 0.85. Voltage drops across both. I equals 18.2, and the sum should be 0 around the loop due to the loop rule. Real values add up to 0.35. Voltage drops across wires and through meters, 18.11 amps across a 100 ohm resistor and 50 amps in parallel with R2. Some results of this experiment was that our R1 was 46 ohms, our R2 was 98. Our R wires came out to 1.9 ohms, and our R ammeters was 0.12 ohms. Constants that were held under this experiment was our VS is about 3 volts with the two 1.5 volt batteries. R1 is about 47 ohms. R2 is 100 ohms. So here's some experimental images of the experiment that we conducted on the virtual lab, and the the experimental data in the form of a graph here. So the RC circuit experiment, so we set up this, the procedure was to set up this circuit with a capacitor, a resistor, and a voltage source. Capacitor charges and discharges. The light dims over time. Lower resistance means a lower charge and discharge time. Results of this is that a 20 ohm bulb had a 62-second charge and a 46-second discharge. A 10 ohm bulb had 11.44 charge and 11.63 discharge. Constants that were held under this experiment was our C was equal to 1, our R1 was 10 ohms, and our R2 was 20 ohms, and our VS is equal to 3 volts. Some discussions and conclusions. So the results compared to our predictions were, we had correct predictions, as actual loop resistance calculated will be greater than 0, and higher resistance yield longer charge over discharge and discharge time. However, as always, there's always error that exists, and so some sources of that could be our human error, just we can't be totally perfect. Some rounding errors, we can't be totally precise. The resistance of the wires, maybe some depleted batteries, and inexact resistance of resistors. Some discussion, though, to be held is, what if you charged a capacitor with no resistor in the circuit? In the ideal model, charging a capacitor without any resistor means R equals 0, so T equals 0. Thus, the capacitor would be predicted to charge instantly. In real life, that does not happen because the circuit still has small resistances from the wires, battery, ammeter, and the capacitor itself. So the capacitor charges very quickly, but definitely not instantly. The measured time is longer than the ideal prediction because the real circuit is not perfect and has a small non-zero resistance. This concludes my lab. Thank you so much for watching.